Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
So lecture 103, capacitance and high voltage breakdown. So let's recall first that if I have a plate of charge and I create a Gaussian surface through this, we'll call this surface A1 and this surface A2, right? Recall that we would get that A1 plus, well, I just call it EA1 plus EA2 is equal to 4 pi k times sigma, where sigma is the charge density. This means that if A1 and A2 are equal in area, right, then we get that 2EA equals 4 pi k sigma, which means that the electric field is equal to 2 pi k, oh, and this is not sigma, this is charge. I jumped the gun, guys. Charge. Q over A, so this becomes sigma, 2 pi k sigma. But because we're talking about capacitances today, we're going to introduce a new measure, and for that reason I'm going to get rid of k as our constant and reintroduce the permittivity of free space through this relationship here. And I'll talk more about that shortly. But if I introduce that in here, then we get that E is equal to, this will give me sigma over 2 epsilon naught. Okay? So that is the field due to a plate of charge, right? So we're going to use that, and I'm going to describe a capacitor now. Oh, that's not the best looking plate. Put some positive charges on this one. It shouldn't be so thick. I'm drawing terrible. Negative charges on this plate, right? So this is a capacitor, right? It's two metal plates, right, in which we've separated charge. Okay, we've got positive charges over here, and we have negative charges over here, right? And in between we have, air. Later we'll talk about putting some dielectric material in there, some kind of insulator. But just suffice it to say that charges are not freely available to travel across this gap, okay? And the distance here will be d, okay? So let's consider a couple of things. First, let's put a Gaussian pillbox around this section of the capacitor, okay? And so remember that Gauss's law says that the flux through the Gaussian surface is equal to or proportional to the charge contained inside. There is no charge in here, right? Because there's an equal amount of, if I assume that the charge density on both of these plates is equal, except that these are negative and these are positive, then they will cancel each other out. And so since the charge inside here is 0, that means that the electric field is 0, okay?
What's that writing underneath K equals 1 over 4 Gauss?
This? Yeah. 1 over 4 pi epsilon naught.
Okay.
Okay, so, but now let me consider two other Gaussian surfaces. These are just like this, right? So we know what the result of this is, yes? This is going to be sigma over 2 epsilon naught. This will be minus sigma over 2 epsilon naught because of the charge, right? So the electric field in between the plates, so this is the electric field outside the plates. Outside the plates, okay? So that's here and here. But inside the plates, in this area here, we have the electric field from this one like this, and the electric field from this one is directed into it like this because it's negative charges, right? Yeah. So we can write that E inside, I guess I should have written E outside equals 0. E inside equals the electric field from the positive plates minus the electric field from the negative plates because it's pointed in the opposite direction, right? We're going in this way, right? So if I add these terms in, this formula here, we'll get sigma over 2 epsilon naught minus negative sigma over 2 epsilon naught. Minus times minus is positive, so this gives me sigma over epsilon naught. That's the field inside, in between the plates of the capacitor, okay? And so that is going to be, I'll call this a parallel plate capacitor. E equals sigma over epsilon naught. Now let's talk about the potential, and the electrical potential between these two plates. So delta V, which is going to be V plus minus V minus, the potential at the positive plate minus the potential at the negative plate. So we're just going to call this V, by the way, but for now I'll write it like this. So what is this equal to? Well, potential, right, How do we evaluate that? We have a constant electric field, right? Remember, the electric field is just the force per charge, right? And so to calculate the work, we would have to do force times distance. So to calculate the potential, we just need the field times the distance. But the field we have from here, right, that's just equal to sigma over epsilon naught times the distance. And sigma is just charge per area, right? So I'll write this as Q over epsilon naught A times D. I'm just going to rearrange things just a little bit. I'm going to write this as D over epsilon naught A times Q. I actually want to solve for charge. So I'm going to write this as Q equals epsilon naught A over D times V. Okay, I just solve for Q in terms of V. Instead of writing delta V, I'm just writing V. Okay? So why did I do that? Well, because of capacitance. So we define this new term called capacitance. C, don't confuse it with the speed of light, but right, you wouldn't, because it would always be associated with charge and voltage, right? So this is a measure of, so if these are volts and these are charges, right, this is volts and coulombs, so this must be a measure of coulombs per volt. So it's how many coulombs per volt you can store on the capacitor, okay? And so that's what this thing measures, and this, for a parallel plate capacitor, right, it tells us that the capacitance is equal to, and I'll write PP for parallel plate, is equal to epsilon naught A over D. How did I get that? Well, if you just look at these two equations, Q equals this times the voltage, you can see that C must be playing this role right here, yes? So that's how I, came up with this equation, right? Now you could do it for other configurations. This is not the only capacitor that you could make, and I will just summarize up here. All right, so I'll just maybe draw a little picture of the parallel plate capacitor here. But we could also have a cylindrical capacitor, and that would look, it's like if you've ever seen a coaxial cable, where we've got, I need to draw it bigger. It's not going to ever be enough room. Or if we have this, we'll call this maybe A, radius A, and then we'll have radius B on the outside of the coaxial cable. And usually there's also a cladding that goes around this as well. So coaxial cable is a metal wire surrounded by an insulating material surrounded by another metal container. This is also, what do they call these things? Leyden jars. You get a piece of glass, right? And you put metal on the outside of the glass. You just coat metal around the outside of the glass through sputtering, and then also on the inside of the glass. Or you could just simply drop a metal rod down inside the jar, and you can use that as a capacitor. This was like the first capacitor. They were called Leyden jars because they were invented in Leyden, Germany, I think. But anyways, the formula for the capacitance of this, I never did write this one down, did I? C parallel plate is equal to epsilon naught A over D. And C for the, we'll just call it the cylindrical capacitor, is equal to 2 pi epsilon naught L, where L is the length of this thing, divided by the natural logarithm of B over A. What's the radius of the outer section, the radius of the inner wire. And finally, you've got a spherical capacitor. If you imagine two spheres inside of each other, obviously you have to have some way to get to the middle sphere. This will have, call this R1, and we'll also have radius R2. The capacitance for the spherical capacitor is 4 pi epsilon naught R1 times R2 over R2 minus R1. And there's a rare case where you can let become what they call an isolated spherical capacitor, where you let the R2 become infinity. That will basically just be, I'll write C iso, I might put it as a homework assignment, just times R1. But let's focus on this for just a second and see what we see about this, right? We see that the capacitance is proportional to the area and inversely proportional to the separation distance, okay? So you might ask, how can we make a bigger capacitor? What if we have, we don't want to make a giant capacitor. Maybe we just want to put together a bunch of smaller capacitors. So the question, how can we increase that, right? Well, if we can increase the area, then we can increase the capacitance, right? Whereas if we increase the separation distance between the charges, then we would decrease the capacitance, okay? And so this kind of brings us to an important consequence in terms of what will become part of electronics. So there's two ways we can put capacitors together. We can do them in parallel, or we can do them in series. So what does that mean? would be some parallel capacitors in parallel. C2, V plus, and we'll call this 0 potential. We'll usually consider the negative plate to be the 0 potential. That's where we're going to define the electric potential to be equal to 0. So this would be the negative plate, and this would be the positive plates. And in series, what would this look like? You would have V plus, this would be the positive plate, negative plate, positive plate again, negative plate, and this would be 0. And we could call this C1, C2. So what is the capacitance, the effective capacitance of these two combined capacitors? So we could write that the effective capacitance is equal to the charge divided by the voltage. What's the charge here? What's the sum of the charges on these plates, right? So we've got the charge on plate 1, Q1, plus the charge on plate 2. The potential difference is the same for both plates, right? So there's a common voltage under here. But this would just be VC1 plus VC2 divided by V, which means that this is just equal to C1 plus C2. So the effective capacitance for a parallel circuit, if we put capacitors in parallel, is the sum of the capacitances, so we can add, okay? Well, in series, we'll just define a few regions here. We'll call this V1, V2, and V3. That's the potential in these regions, right? Remember, where you see things connected up with a metal wire, the potential is always the same, right? So the potential is the same here as it is here, because these are metals and the electrons can move around such that they are now equal potential surfaces, okay? So we have an equal potential surface here, here, and here. So that's 3 of them. So to get the potential difference between these areas, V1 minus V3, we'll write this as V1 minus V2 minus V2 minus V3. V1 minus V2, well, that's just going to be Q over C1. And then between the V2 minus V3 is going to be the charge divided by Q2. Did I have a sign problem? Yes, I do. We'll add these. So that changes this to this. So this is equal to the total charge Q divided by some effective potential, or divided by some effective capacitance, where the effective capacitance is equal to 1 over C1 plus 1 over C2, which you could also write as the product C1 times C2 over C1 plus C2. Okay? If you had N capacitors in series, right, then it would be 1 over C effective is equal to 1 over C1 plus 1 over C2 plus ... 1 over C to the N. So you can see that by adding capacitors, you actually decrease the capacitance. So let's summarize that with the parallel and the series circuits. So here, with the parallel circuit, right, D, right, is constant. That's not changing. It's always staying the same charge. The charge separation doesn't change, but the area increases. Okay, and so you're able to add capacitance. Here, the area is constant, but D increases. So the charge separation increases, right? As we add more and more series capacitors in, we increase the charge separation, and this causes them to diminish the capacitance, right? Because of the inverse proportionality to distance, okay? So this is how capacitors add in parallel and series, and that will be important for electronics. One last thing I should mention, I think I forgot to mention it, that capacitance, right, though it has units of coulombs per volt, we've defined 1 coulomb per volt to be equal to 1 farad, named after Michael Faraday, okay? So the farad is the unit of capacitance. Typical capacitances, if we let the surface area of the capacitor be on the order of a square centimeter, and we let the separation distance be on the order of a millimeter, then we're looking at capacitances in the microfarad regime, just to give you an idea. So if you use a capacitor in electronics, it's going to be some number of microfarads at most, probably more likely picofarads, in fact, okay, for smaller capacitors. Now I want to talk about charging a capacitor and the amount of energy that is required to charge it, right? So we're looking at how much work do we have to do. And so if we think of the parallel plate capacitor as our model, we've got the positive and then the negative, right? We're thinking about moving positive charge from the positive plate to the negative plate, and that's going to require work, right? How much work does it require? Well, it's going to require the potential times dq, the little amount of charge that we're transporting. du, the change in potential energy, is equal to v dq. the little amount of charge that we're transporting across, right? So the change in potential energy is equal to the voltage across these plates times how much charge we're transporting. But this we can express as Q, the charge, over the capacitance. And dQ again. So we can integrate this from 0 charge to as much charge as we're going to put on the capacitor, right? So the capacitor starts out with no charge, and we're going to put, let's say, Q naught amount of charge on it. And so that's Q over C dQ, which is just 1 over C times the integral from 0 to Q naught of Q dQ, which is equal to, well, the integral of Q dQ, right, or x dx, right, is just going to be 1 over 2, so 1 over 2C times Q squared, evaluated between 0 and Q naught, so it's going to just give us Q naught squared. But since Q is equal to C times V, this implies that Q naught squared is equal to C squared V squared. So I can substitute that in here, and we'll get that the potential energy is equal to C V squared over 2. Now notice that I never used the formula for the parallel plate capacitor, even though I used it as my example that I was thinking about as I calculated this work, this potential energy. This is actually a universal result for all capacitors. This one, this one, this one. So this is the energy required to charge the capacitor, but it's also the energy in the electric field between the capacitors, okay? And so I want to look at that next. So now I'm actually going to use this geometry, right, where the electric field is equal to sigma over epsilon naught. So the work to move a charge across here, right, is going to be E times D, well, this is D, of course, just like before, times dQ. But let me rewrite this as Q over epsilon naught A. And now I want to differentiate this. Right? I want to get dE dQ is equal to, well, the derivative of that would just be 1 over epsilon naught A. But that implies that dQ is equal to epsilon naught A times dE. So I want to replace this dQ with this equation here. So we'll have E times D times epsilon naught A dE. So see, before I found the potential energy for charging a capacitor without directly using the properties of this capacitor. Now I am. So we can calculate the work by integrating this whole thing from 0 to E naught. We'll start out with no electric field, right? And we'll increase the electric field between the plates of the capacitor to some amount, we'll call it E naught. And that'll have all of this in it. We'll have E times D times epsilon naught times A dE. But most of this stuff is just constant, so we can pull that out. D epsilon naught A we can pull out. And we're just left with 0 to E naught E dE. And when we evaluate that, we're going to get 1/2 D epsilon naught A E squared, or E naught squared, minus 0, just doesn't change it. If we look at, I'm going to move this around just a little bit. I want to move the D right next to the A, epsilon naught, because what is D times A? Well, A is the surface area, right, of this plate, and D is the separation between them. So you can see that this D times A, right, is actually a volume, which I'm going to write with a funny V like this, and that's equal to D times A. So if I do that, what do I got to get the work? Equals 1/2 epsilon naught, this funny volume, E naught squared. Now I want to define basically an energy density. I'm going to call it U, and I'm going to write with a funny script U, which is going to be W over V, right? Or really, it's just potential energy over V, right? Regular U over V. Because the potential energy is equal to the amount of work it takes to move that charge in the first place, right? So these are equal. And so that is going to be equal to 1/2 epsilon naught E squared, I'll call it. And that is the energy density, right? So that's the amount of energy stored in the field in between the plates. And so I suspect we'll use that later, okay? It's an important result, especially when we start talking about light and we want to talk about the energy density of the electromagnetic field. Yeah. All right, now on to the last thing. All right, so now to talk about the dielectric breakdown, okay? So Benjamin Franklin invented the lightning rod. You're probably familiar with Benjamin Franklin, yes? People often think that he was regarded as a famous scientist because he was a famous statesman, but it's actually the other way around. He was a famous statesman because he was a famous scientist. And among his many contributions, one of them is the invention of the lightning rod. The British, however, during the same time period, thought that the better way to make a lightning rod was so he liked to make them with a pointy tip. And the British thought it would be better to put a rounded ball on top. And so we're going to kind of look at why it is that rounded ball is not as good an idea as a more pointy tip. All right? So I want to think of kind of a cam-shaped piece of metal, right? And about what the electric field looks like in various places. But the way I'm going to do it is by approximating these regions. I want to draw that again. That's terrible. So I'm going to approximate this cam shape by two circles. One with a smaller radius, we'll call it r, little r, and one with a big radius, which we'll call big R. And then of course we can, get rid of this part here and just simply connect them with a wire, right? Why connect them with a wire? Well, because we want them to have the same electric potential. So if we connect two pieces of metal with a wire, they will then be at the same electric potential. It forms an equipotential surface. Because of the unique nature of metals, the electrons move around such that the electric field inside of them will be zero, and this will give them the same electric potential. So one of these, I'm going to give you a problem on your homework, and I guess I'll think about it, which one is going to be. Which one is easier? Well, I think the one that's more relevant to our point is to calculate which one of these has the higher electric field, okay? And so I'll do that one in class, and I'll have you in your homework decide or calculate, or show rather, that the charge density will be higher on one of these two spheres than the other. So let's look at the electric field. So we can kind of think about it, right? If we think of the electric field coming out of here, right? And then out of here. If I were to take a small area, like say this, right? You see that I get three field lines through it over here, and this is at a distance, let's say d, away from the sphere, okay? If I put the same surface a distance d away from this sphere, then you can see that we only get one field line through it, okay? So you can kind of see graphically or geometrically why it is the electric field will be higher around this smaller sphere than this larger sphere, okay? But we can do more than that. If I consider the ratio of the electric fields, E sub r over E sub big R, that's the electric field from this. This is the electric field from this. This is going to be roughly the charge over r squared divided by, this is qr, q big R over big R squared. And so that is going to say q big R, q little r over q big R times big R squared over little r squared. But we need to get an expression for the ratio of the charges, and we know that the potential is the same. Potential at VR is equal to the potential at big V, V big R, which is to say that Q sub little r over R is equal to Q sub big R over R, which implies that QR over QR is equal to big R over little r. Except that I wanted the other one. I wanted QR over there. So we just want the inverse of that, which I can then substitute in right here, right? So that's little r over big R times big R squared over little r squared, which just gives me R over R. This tells me that the electric field for the small sphere is equal to big R over R times the electric field at the big sphere. And since R is greater than R, this means that E sub R is bigger than E sub big R, right? Because the relationship between the electric field for the small sphere and the big sphere is that the small sphere is the ratio of the radii, big R over little r, times the field here. So whatever the field is here, the field here will be bigger by the amount big R divided by little r. So for example, if big R was say 4, little r is 1, then the electric field here would be 4 times as much, okay? So you have a stronger electric field. And why does that matter? Well, because there's something called dielectric breakdown, and we're not going to go into a great bit of detail on it. But the general idea is that if you build up a strong enough electric field, then even air can become a conductor. It will ionize the air because of the strong electric field, right? And that will allow current to flow. So if you've ever seen any of these spark generators, have you ever heard of a spark plug in an automobile?
Yes.
Yeah? It's got two pieces of metal. You put a big potential between the two, right? It's like a capacitor, but the voltage is high enough that it causes dielectric breakdown, okay? So you can get really strong electric fields, and it just makes air into a conductor, and you get a spark, and electricity travels through the air, okay? So that's more likely to happen near the small sphere than the large sphere, because the electric fields here, once you start to build charge up on them, can become very great, you see?
Yeah.
Okay? So when you have lightning, right, you have, well, in general, the ground is actually negatively charged because of the lightning strikes. So we always have an electric field on Earth of something on the order of 100 volts per meter, which seems weird, but it is true. What happens is up in the clouds, as different air rubs over itself, right, you get these charge buildups, right, and you get a large discharge, right, so you get very large number of negative charges up in the sky, right. This is going to cause positive charges to accumulate around the tip of your lightning rod, and eventually the voltage difference between the two will become great enough that you'll get the dielectric breakdown and lightning will form, basically. That's an overly simplified version of it, but that's generally the idea. Okay, so the sharp points, right, can afford much larger electric fields and will therefore facilitate dielectric breakdown. Anytime any of these chain reaction type events take place, whether it be condensation or any kind of precipitation, it always requires some seed, right? So, I mean, you could, for example, heat water up to a very high temperature, right, well beyond its boiling temperature, as long as it's pure. But any little impurities, a little piece of dust or something like that, will act as a precipitation point or a condensation point, which will set the whole thing off and it'll start boiling rapidly. And lightning is kind of the same way. And so that's the way I think of lightning rods anyways, is they're the kind of the precipitation points for electrical current to flow from the sky down to the ground. And it's because of all these lightning strikes, roughly 100 per second worldwide, that results in this negative charge that we have on the surface of the Earth, giving us this electric field of 100 volts per meter. I think that's all I had on that, okay? So generally you don't take your capacitors up to a high enough electric potential to get dielectric breakdown, but you could. You can take a capacitor and apply a large voltage across it, and it'll pop. But that's, of course, not what they're intended for. They're intended for storing electricity, or electric charge, rather. And so that's what we mean by capacitance. It has a capacity to store electric charge. And that value is given by its capacitance, which I calculated for several things here. Any questions? Sorry about the voice. I still haven't quite recovered from my sickness, but it's getting better.
About that picture there, what's that line which...
This?
Yes.
Well, I just said, well, let's consider, to get an idea of the field strength, we'll create a surface and see how many field lines go through it. Right? So if I put this surface a distance d away from the small sphere, I see I get 3 field lines through it in my drawing, whereas in the big sphere I only get 1. Remember that the density of field lines is how we measure the strength of the electric field in these pictures, right?
All right.
Yeah, so that's kind of this, and this is the geometrical version of it. This is the algebraic version of it, okay? And so what I'll ask you to do in your homework, since I did this, is to show that the charge density on the small sphere is greater than the charge density on the big sphere. That's what gives rise to these strong electric fields, okay? And it's a similar bit of algebraic manipulation that gets you there. Okay?
Okay.
All righty.